In this section, we're going to look at how do we measure distance traveled. This is going to be backwards from what we did earlier in this course when we looked at how do we measure velocity and how do we measure speed. So in this section, we're going to calculate total distance traveled by adding estimates of distance traveled over small time intervals. We're going to visualize distance traveled as area under the velocity curve, compute these things called left and right Riemann sums, and then we're going to estimate the accuracy of these estimates. So first, let's talk about distance traveled in general. We're going to use this formula from physics or from earlier in this course or from other places. Distance equals velocity times time. If you are going 10 miles per hour for 1 hour, you have traveled 10 miles. Velocity times the time. So in this section, as I've kind of said, we're going to be given information about velocity, and we're going to go backwards from what we've done, and we're going to try to determine distance given velocity. And this is all moving forward to Chapter 5, Chapter 6 material, which is looking at antiderivatives, and we'll see how that's all related in a few sections. So let's start with this example. The table below shows the velocity of a bike moving along a straight road. This idea of a straight road is important right now because if you get to a curvy road or something, it becomes a little more complicated. That's something that you can take care of in a Calculus 3 course. So we're asking how far has the bike gone in 4 minutes? And we're given some information about, again, the velocity of the bike. So we know at the very beginning, the velocity is 0. At the start, we're 0, we haven't gone anywhere. After 1 minute, the velocity is 10 miles per minute. At 2 minutes, we've increased to 14.4 miles per minute, and then 17.3, and then 20 miles per minute for the last few minutes. So if you want to estimate the distance traveled, we can say that this might be, we can use these values and say that maybe for the first minute, we're going to look at just saying that we are going to go 0 miles per minute in that first minute. So during the first minute, we're going to say that we're going 0 for 1 minute. Let me erase that. We're going to go 0 miles per minute for 1 minute. And this may not be very interesting, but this just means we've gone 0 miles in that first minute. Maybe the next one's going to be a little more clear what we're going to do. If we think about now, we're going to add how far we go in the second minute. So this is, the first minute is from t equals 0 to t equals 1. Now we're going to go from t equals 1 to t equals 2. That's the second minute. And now maybe we can use the next value. We know at t equals 1, we're going 10 miles per minute. And we're going to do that for another minute. And we're going to keep on this process. We can now add how far we're going to travel during the third minute. That is from t equals 2 to t equals 3. And we're going to use this 14.4. And again, we're going to travel for 1 minute. Let's do a few more. We could then talk about how much during the fourth minute, that is from t equals 3 to t equals 4. That is the last minute we're going to do. And we could use this 17.3 miles per minute. And again, we're traveling for 1 minute. So what we're doing here is we're using one of the velocities given to say that we're going to go that velocity for the entire minute. Now, that's not what's going to be happening. It's not like you go 0 miles per minute for the first minute and then you jump to 10 miles per minute. But with the information we're given, that's a good estimate for how we can go about this. So, first of all, note that if we did add all of these up, we would get 41.7 miles. And note that in this, you can see the minutes are going to cancel out in each of those. We're going to be left with miles in all those calculations. But that is not the only way to go about this. So another way that you could estimate distance is looking at the same time intervals. Looking at the first minute, why do we have to use that first value of velocity? We could instead use that second. Right, so for the first minute, we could use the 10 miles per minute times 1 minute. For the second time interval, we're going to use that 14.4. For the third, we'll use the 17.3. And for the fourth, now we'll use this 20. And if we add all of these up, we would get a different value. This would give us 61.7 miles. Now let's think about this problem a little bit more. Here we have that the velocity we're going is increasing as we're going. We start at 0, then we go 10, 14, 17, 20. We are getting faster as this is going on, or the bike is going faster. So in our first approximation of distance, we use the lower value each time, the left value. And that gave us kind of an underestimate for how far we might be going, right? If we had to choose between 0 and 10 to estimate that first minute, we used the lower one. Whereas in the second one, we used the higher one. That gave us an overestimate. So here we can say that the actual distance traveled is going to be trapped in between the 41.7 and the 61.7 miles. We're going to say that this first one is an underestimate, and the second one was an overestimate. So how can we find the actual distance traveled? We can't with this information, but we could make a guess. Maybe it's halfway in between, right? Maybe it's 51.7. Maybe that's a good guess. And there's not really a right answer because we're just estimating it. All right, let's think about this example, but in a different sort of sense. Now we're going to think about it graphically. We're going to think about v of t, where this velocity is a function. Again, we'll say this is velocity. We'll call it v of t. And now we can think about these as function values. And what we're really looking at when we did this calculation is we found areas of rectangles. So let's remind ourselves of some of the calculations real quick. In the first one, we approximated the distance traveled as 0 times 1 plus 10 times 1 plus 14.4 times 1 plus 17.3 times 1. And these are areas of rectangles. These ones are the base or the width of the rectangle. We're going to call this delta t. It's the change in the time. And that's going to be just 1 minute here. And that doesn't change even when we do the other part as well. So that means if that's the base of the rectangle, these speeds, these velocities, are the heights of the rectangles. And we can visualize those given here. We have our first rectangle is not really a rectangle, it's just a 0 rectangle. Our next one is a height of 10, base of 1, and we know that that area is 10. The next one has an area of 14.4 and then 17.3 for the last one. And we are adding up those areas, and that's going to be an estimate for how far we've gone. On the reverse side, if we look at the other way, then we use the right values each time. And that gave us 10 times 1 plus 14.4 times 1 plus 17.3 times 1 plus 20 times 1. And again, we have our base of our rectangles is 1 in each of these cases. Right, we have the base of the rectangle in all of these. And now the heights of the rectangles are these other values, the 10 and the 14.4. 10 is our first one, 14.4 our second, 17.3 our third, and 20 our last one. And we're adding those up. And we might be able to see kind of what we're sort of getting at is that what we're really going to be looking for is the area under this velocity function. And we're estimating that area with these rectangles. And we can see on our first one with the blue that our rectangles are always below the velocity curve. And that means that we're going to have an underestimate, right? There's some parts that we're not going to be getting, right? We're not counting these shaded areas here. That's an underestimate. Whereas on the other side, we actually are doing too much. We have some stuff above the function that we're counting, which we shouldn't. That is an overestimate. So these two slides have done the exact same calculation, just two different ways of thinking about it. Algebraically with these multiplication of numbers, or not geographically, geometrically thinking about these areas of rectangles. All right, so now we're thinking about an estimate of this distance. Now let's think about improving this distance estimate. And one way to do this is if you had more data, right? If you knew your speed, not just at every minute, but every half minute, then you can get a better estimate. So now we know, for instance, at 0.5 minutes, at half a minute, we know what our speed was at that point. And that gives us more information, which allows us to get a better estimate of what's going on. And that's always going to be the idea. If we have more data, our estimate of distance would get better. If somehow we knew the velocity at every second, right, we could add up a whole bunch of numbers and get a very good approximation for how far we've actually traveled. So let's do one of these estimations real quick. Or maybe we'll do both real quick. So the first one is going to be, we're going to take the left point. So we're going to say that we're going to go 0 miles per minute for how long? Now just for half a minute. No longer doing the entire thing, just half a minute there. And then we'll do 7.1 for the next half a minute, and then to save some space, we're going to continue. We're going to continue adding the 10, the 12.2, the 14.4, the 15.8, the 17.3, until we get to the very end. We'll do 18.7 miles per minute times 0.5 minutes. And if we add all of those up, we would get 47.75 miles. So here, our delta t is what we're going to call this 0.5. That's the change in time. Here it was half a minute instead of a full minute. And we also have 8 things that we're going to be adding up, 8 half a minutes that we need to look at instead of 4 full minutes. If we did this the other way, we would use the left point, so we'd go 7.1 times 0.5 plus 10 times 0.5. And then we keep on doing this until we got to our last one, which we'll use the 20. And if we added all of those up, we would get 57.75 miles. So again, this is an overestimate and an underestimate. Not in that order, the opposite order. So our first one was an underestimate. Our second was an overestimate. And we can say that the distance traveled, the actual distance traveled, is somewhere trapped in between those estimates. We have our 47.75 and our 57.75. So what's the actual value? Maybe it's exactly halfway in between, but we don't actually know. It could be exactly that. It's hard to say for sure. But we now have taken our interval that we've had. We went from like 41 to 61, and we've brought it in and we made it more and more accurate. And with more data, we'll continue to do that. If we look at the pictures here, now we have 8 rectangles that we're drawing instead of 4, because we have 8 half minutes that we're talking about. But again, we can see that the first one here is an underestimate because we are leaving space underneath the curve that's not being counted. Whereas the overestimate is counting too much so that's an overestimate. And again, we're using some velocity function, v of t, and looking at function values of the velocity function. So how can we get a better estimate than this? Again, what if we looked at not every half minute, but every quarter minute, or every 10th of a minute, or how about every second, every 60th of a minute? Can we go further than that? Absolutely. We could look at every nanosecond and really get to this point that we could estimate it using any number of rectangles or any number of time intervals. And that's how we're going to get our integral we're going to define in our next few sections. In the meantime, we're still going to think about estimations. So now let's look at distance traveled as area. So we're going to say if velocity is positive, like in our last example, the distance traveled is going to be the area under the velocity curve. And in general, that's what's going to be the case. We're going to have our distance traveled is the area under the velocity curve. There's one little caveat, and that is if velocity is negative, then the distance is still the area under the curve, but now we can think about displacement how, like, what's the change in position? That's what displacement is. Is the signed area under the curve. That is, if you're below the x-axis, then we have negative area. If velocity is positive, then displacement is the same as distance. This is the exact same idea as velocity and speed are the same if we think about positive values. Once you start thinking about negative values, they're a little bit different. So let's look at this picture here. We have our velocity function v of t, and this velocity function is both positive and negative. That means if we're thinking about a car, if we're above the t-axis here, that we are going forward, we have a positive velocity. If we are below, that means we are going in reverse. We're having negative velocity. Think about a ball being thrown in the air. Negative velocity means we're going down instead of going up. Right? Think about a car, it means it's going in reverse. So if you think about how far has has a particle traveled or a car traveled in this example, then we can say the distance traveled total is 4 feet plus 3 feet. There's been 7 feet traveled total. That's the area, the distance underneath the first chunk, plus the area of the second chunk. If we think about the change in position, then that is going to be 4 feet minus 3 feet. We've only gone 1 foot total. So what's happening here is we have maybe some car, and it's going 4 feet, and then it's turning around or going in reverse 3 feet. And we're going to graph that velocity. We are increasing the velocity and then decreasing the velocity, going from 4 to 1. So total change is 1. Total change in distance, how far we traveled total, is 7 feet. We're going to be thinking mostly about change in position. This negative area has to be included, right? This area here for 3 with the red, we can think about as negative 3 feet if we're thinking about the correct circumstance. And that's what we're going to usually do. So now we're going to define what we've already done in this video, the left and right Riemann sums. So in general, we're going to let v equals f of t. That's the function we're dealing with. That's the velocity function. We're going to be given velocity values, and we're going to try to estimate distance traveled. So to estimate this from time t equals a to t equals b, so on some time interval, we're going to find the velocity at a certain number of points. We're going to call that n points at consistent intervals, delta t. And the delta t here is, again, the same delta t we used before. It's going to be a formula we can use as b minus a over n. That is the total time that we're looking at over the amount of time intervals that we have. Right, this b minus a is the total time, and n is the number of intervals. So if we go back to some previous examples for a second, in our first example, we said delta t was 1, but we could also say this is 4 minus 0 divided by 4. We have 4 different intervals that we're looking at, the first, the second, the third, and the fourth minute. And our b and a values, a was 0, b was 4, and that gave us a delta t of 1. In our next example, we have that a is 0, b is 4, But this time we have 8 intervals that we're looking at. So then each time interval was 0.5 or half a minute. So now where we're at, we're just saying in general, we're going to have the total time that we're looking at, b minus a, divided by the number of intervals or number of points we're going to look at is our delta t. It's our change in time on each interval. And we're going to look at the velocity at a certain number of points. So here we have our n points that we're going to be looking at, our nt values, and we're going to have t sub 0 be our first one, and then we're going to label those all the way up to t sub n minus 1. All right, we're not going to label up to t sub n. This is a little bit tricky thinking about. You need one more point for one less interval. We'll kind of see it in an example what I'm talking about here. We're going to label from t sub 0 to t sub n minus 1. A is the exact same thing as our first value. B is the same thing as our last value. So if we're thinking about rectangles now, we're going to take these intervals and we're going to have rectangles for each of these. That means we need to find the height of the rectangle and multiply it by the base. And the base is the same for all of these. It is delta t for all of these intervals. It's the height that changes. And if we're doing the left sum, that's the first one we did. That means looking at the first point. Then we are looking at the left point on each interval and looking at the function value there. So we're going to take f of t naught plus f of t1 plus f of t2 plus all the way down to f of t sub n minus 2 times delta t in each case. That's what we did in our first example, looking at the left endpoint. As opposed to looking at the right endpoint, f of t1, f of t2, f of t3, and f of t sub n minus 1 if we go all the way out. That's what we call the right Riemann sum. These are also called the left sum or the left-hand sum or the right sum or the right-hand sum. There's a lot of different names for those. We're going to use Riemann sums for us. Remember that these are estimates of the distance traveled. So note that if our velocity function is an increasing function, right? So let's think about if v is increasing, that means it's going up from left to right. The left Riemann sum from A to B is going to be an underestimate. So we're going to use the left point to draw our rectangles for each of these. So notice what I drew here was an example where n was equal to 4. We had 4 rectangles, and we're using the left endpoints. I could draw a picture on the same graph of the right endpoints. And that would give an overestimate. So an increasing function, a left Riemann sum is an underestimate, right Riemann sum is an an overestimate. I think I did that backwards, sorry. If the velocity function is increasing, then the left one is an under, and the right one is an over. And if it's a decreasing function, we have the opposite, over and under. And we can draw that as well. If we have a decreasing function, oops, that's not decreasing, decreasing function from A to B. Let's do an example where n is equal to 3. The left Riemann sum will be an overestimate, and the right Riemann sum will be an underestimate. And we can say the difference between the left and the right Riemann sums is just going to be f of b minus f of a times delta t. And why is that true? Let's go to the previous page. The only difference between the left and the right Riemann sums are the first term in the left and the last term in the right. These are the only terms that are different between the left and the right. So if you took the left and you subtracted the right, everything would cancel out except for that first one and the last one, and you'd be left with f of b minus f of a. So that is the difference between the sums, and that gives you an idea of how accurate your estimate is. Note that that's only true if the velocity is increasing or decreasing. It gets a little more complicated when it's not like that. But for this first part of the chapter 5, we're just going to be thinking about increasing and decreasing. If f of b and f of a are very close together, then that's going to be a good estimate. If delta t is really small, that's going to be a really good estimate. And either one can help us out there. In the next video, we'll look at some practice problems relating to finding left and right Riemann sums and talking about the estimations as well.